Hello, can you hear my voice? No.
Yes, doktor.
Boleh dengar tak? Tapi kenapa saya tak boleh dengar nama apa? Suara awak. Sekejap, saya tengok. Okey, boleh dengar tak suara saya?
Boleh doktor.
Boleh, doktor.
Suara awak. Sekejap, saya tak dengar suara awak. Sekejap lah. Apa yang terkena ni? Okey, boleh dengar suara saya? Tolong respon sekejap.
Boleh doktor, boleh.
Dah mesti tak dengar lah. Sekejap Okey, boleh dengar suara saya?
Boleh doktor, boleh.
Tolong cakap.
Doktor boleh. Can.
Boleh dengar?
Boleh.
Tapi saya tak dengar lah suara awak. Nanti takut awak tanya saya tak dengar. Sekejap Saya betul setting kat mana-mana ni. Okey, saya keluar balik. Nanti saya masuk semula. Awak tunggu dalam ni sekejap. Okey, boleh dengar suara saya?
Boleh, doktor.
Alamak. Alamak, saya still tak dengar suara awak lah. Ya, last time. Kalau tak, lepas ni awak dengar. Saya tapi awak tanya soalan, saya tak boleh dengar. Susah saya. Okey, boleh dengar suara saya sekarang?
Boleh doktor, boleh. Dengar.
Okay, at last. Okay, good. So, okay. I apologize for the for the delay. Okay, so please wait. I'm going to give you the QR code for the attendance. Okay, so please scan your attendances. Okay, dah. Semua dah ni. So kalau semua dah scan, saya akan deactivate sekarang. So malam ni ada yang ada test Malam ni ada yang ada test tak? Saya tanya ni. Oh, okay. Okay, good. So, pula belum scan lagi. Scan cepat. Saya nak deactivate ni sekarang. Cepat, Zat. Okay. So I'm going to deactivate right now. Okay, nampak saya punya slide? Can you see my slide?
Yes, Doktor.
Okay, okay. Okay, so basically, we are at the, we already finished doing the derivation on the half-car model during our morning class today. So today, for tonight, we're going to continue on the derivation for the full car model, where in full car model, we're going to have 7 degrees of freedom. Okay, before that, if for those who would like to play around with the equation of motion for the half-car model, you can start developing this model in block in MATLAB Simulink for the purpose of practicing the Simulink block. Okay. Before that, let me give you some parameters value for this one. For half car model, this slide. So basically, all the KS use the same thing. So you use the MS, go 250. No, for half car, it's going to be double. Okay. So we use 500 kilogram. For MU, we use 50 kilogram. Still the same. For KS, we use 17,900. Okay, Newton per meter. For CS, we use 1,500 Newton second per meter. KT, we use for 179,000 Newton per meter. So for this one, we have for we're using example for rule. So it's going to be for the front right, front left, right, and front left. This one also is the same thing, front left and front right. Same thing, okay. Okay, use this parameter value if in case that you want to start developing simulation model of a half car model in MATLAB, using MATLAB Simulink. So any question on the half car model before I'm going to continue with the full car model? Okay, kalau tak ada, kita continue. Okay, full car model. Okay. Assume that for full car model, of course, we're going to model the vehicle as at a full scale using the actual weight, using four corner. We're going to have this four corners at the chassis. So we're going to have front left, front right, rear left, and rear right. So we're going to model it just a simple. We don't just a simple block. So this. have okay. So over here, we have the L, and we're going to assume the distance of CG towards the front axle and the CG towards the rear axle is L over 2, where we're assuming that the CG is actually at the middle. Okay. And then for the track width, we're going to use T. Okay, T. So this one is going to be T over 2. Then this one also going to be over 2. So and then for this one, we're assuming that okay, this one is going to be our front right. Okay, this one going to be front right. This one going to be front left. This one going to be rear right. Then this one going to be rear left. Okay. And then in this model 2, we're going to assume that only front left hit the bump. Okay, when only front left hit the bump, so we're going to see that this full car model is actually having both roll motion and pitch motion at the same time. Okay, so meaning that if you okay, let me draw the row input. Okay, let's say that this is the row input for this one. So when front left hit the bump, so if you take a look at the front view, so we're going to see that the front left is going to go up, and then the front right going to go down. And at the same time, if you look at the side view, where we are going to be interested in the pitch motion, so we can see that as if that the front axle is going to go up, and then the rear axle is going to go down. Okay, so this is a full isometric view. Now we're going to take a look at the front view for in terms of front view. Front view. Okay, so we're assuming that okay, for this one the derivation is the same as the as the half car model. It's just that this time instead of having only one suspension, so we're going to consider the suspension at the front and at the rear. Okay, so this is the suspension. Then over here we're gonna be okay. So okay, this one is the CG. So this one is a front left, front left. Then this one is front right. This one we have the KSFL, same thing. So everything we're going to put a label. So we have a KSFL, CSFL. We have a KTFL. Then this one we have KSFR, CSFR, then KT. So, okay, this one is KTFR. So basically, this is actually the one that we see at the front. So we still need to even though that we're not going to label the suspension at the back, so it's still in the figure, and then it's going to be involved in the equation of motion that we're going to derive later on. Because if I put everything in this figure, it's going to be very crowded. Okay, so this one is T over 2. T over 2. Okay. Then for side view, front view, this one for roll, this one for side view. This one for pitch. Same thing, you're going to draw this thing. It's just that you need to change the subscript, okay, and then the wheelbase. Okay. So this one for set view, we're going to have alpha representing the pitch motion or pitch angle, and then for this one we have theta. Okay, the typical notation that we use. Okay, for this one we have KT front right. Sorry, yeah. This one is KT rear right. Then the KS RR front R, CS front right. Then this one we have KS RR, CS RR. Okay, now okay, see the difference between the roll model and the pitch model. Even though that we just label the element that we see in that view. For example, in front view, we actually look at front view for take a look at the roll motion. We only see the front right and front left. Okay, the rear right and the rear left is there, but it's just that we're not going to label in this figure because it's going to look crowded. Okay, And then same goes for the side view, where we are actually using the side view for the you know, pitch motion, where in side view, the only thing that we see from the side, from this one, okay, and this one, for side view, we see the front right and rear right only. Okay. For the front left and rear left, we're not going to put in this one. It's going to be a bit crowded. So is that okay? Going to be involved in the derivation later on. So this one we need to change to the okay. This one going to be, we're assuming that the CG is at the center of the wheelbase. So therefore the distance CG to the front axle and distance of CG to the rear axle is just L over divided by 2. Okay. So any question on this figure? So ada yang tak faham? Kalau dia punya notation subscript tu tak clear ke? Kalau tak clear, hopefully awak faham lah apa yang saya tulis ni. Kalau tak faham, awak baik tanya sekarang. Okay? Faham Awak ni betul ke ni? Hakim. Siapa nama Hakim? Hakim Afifi. Hakim Afifi. Hakim Afifi 1. Hakim Afifi 2.
Ya, doktor.
Hakim Afifi 3.
Hello doktor.
Yang jawab ni Kamarul. Saya panggil Hakim Afifi.
Saya jauh dekat ni laptop dia.
Oh, itu Kamarul Azim mana?
Ada. Saya sebelah dia.
Betul korang ni. Buat apa ni bilik tu?
Tak, kami roommate.
Oh, roommate. Okay. Nasib baik roommate. Okay. Faham figurnya? Ada apa nak tanya?
Faham doktor.
Okay. Lagi nak kena panggil ni korang ni. Naufal Luqmanul Hakim. Naufal Luqmanul.
Yes, doktor. Yes.
Ini pantas, bagus. Okay, Syahid Maidan. Syahid Maidan 1.
Yes, saya doktor.
Okay, ini penyepat, pantas. So ada apa-apa soalan? Faham saya punya figure? Kalau tak faham, pergi tanya sekarang. Nanti saya clear kan?
Tak ada soalan doktor.
Okay. Okay, now we're going to go for the derivation. Okay, for the derivations, this same thing. So we're going to do the free body diagram for each bodies available in the full vehicle model, where we have the chassis, the sprung mass, which is representing the sprung mass for the vehicle, and then we have the arm sprung mass for each corner. We have the arm sprung mass for front left, front right, rear left, and rear right. Okay, and then okay, go back to this one. So this one we have this one is a 7 degree of freedom, where 4 degree of freedom is actually representing the sprung mass, unsprung mass vertical motion. For this one, we have show you. Okay, this one. Okay, this one is a okay. So for unsprung mass, which is for wheel, we have 4 tires, and then that 4 tires is allowed to move up and down. So we have 4 degree of freedom, and another 3 degree of freedom is actually at the center of CG, where we have the roll motion, and then for the lateral axis, we have the pitch motion, and then for vertical motion. Okay, this is actually at the CG. Okay, I'm just draw it outside of the figure to avoid the model is too crowded. Okay, so we have 7 degree of freedom, meaning that 3 degree of freedom at the CG of the sprung mass, and another 4 for the vertical motion of the unsprung mass. Okay, so we have 7 degree of freedom. Okay, now for the derivation, same thing. So we just that one. Okay. So, oh, sorry. Lukis. Lukis. Okay. Okay, now for Sprout Mesh. So for Sprout Mesh, we have the suspension forces. So when I say suspension forces, it's actually comprising of spring force and damping force for each respective corner for the vehicle. Okay. So basically, if I'm going to draw this one, so we're going to have 4 suspension forces. So 4 multiplied by 2, basically we're going to have 8 arrows acting on the free body diagram. It's just that we cannot draw the arrows because by right you're going to impose what the other side you will not be able to see it, but we're just going to draw it. Okay, so for suspension forces, this one. Okay, for this one we have the suspension forces FS front SF front right plus FS front left, and then for this one you have FS front rear right plus FS rear left. Okay, so we're going to neglect the effect of the gravity. So summation of forces. Yeah. Okay, so if we are summing up everything, so we need to write everything lah. So we have the okay, so we have the F. We have the start with the front axle first to make it easy. So we have FS plus FD bracket FL plus FS plus FD. The same thing, we just need to change the subscript. Okay, FR plus FS plus FD R L plus FS plus FD R equal to M S ZS double dot. So this is our the most general equation, number 1. Okay. Next, we're going to have the summation of moment, which is now we are going to look at the this figure. So we're going to have a rotational motion about the x-axis, and then the rotational motion of about the y-axis. The x-axis is the roll motion. The y-axis rotation about y-axis is actually the pitch motion. Okay, so now you can see. Just need to put some imagination by looking at this one. So now for front view, so we're going to have the suspension for the front left and rear left, which is going to create a moment, positive moment. And then this total summation of front right and rear right, going to create the counter clockwise direction of moment. Okay, so we have the summation of moment of what ixx of theta double dot. So by looking at this figure again, so we need to know that the t over 2, so summation of moment going to be, let me change with new color. Okay, so we have a summation of moment go to I x go to theta double dot. So we have f s plus fd t over 2, and then yeah, you're going to create positive f L plus F S plus F D F R. So the whole thing, oh sorry, not F R, rail left, sorry. So the whole thing going to be multiplied with t over 2, which this term is actually moment. This one a moment of in this direction. Okay. So the suspension forces on the right side is going to create the what negative moment, because our notation used right now is counterclockwise is a positive. So we can use this one. So we have the Fs plus Fd for front right plus Fs plus Fd for rear right, multiply with the t over 2, same thing, because we're assuming that the track width at the center. Okay, the track width is always at the center of the vehicle, except for the wheelbase. Wheelbase right now we are assuming that the CG is at the center. So by right, this the wheelbase is not actually at the center of the vehicle. Usually going to be towards the front axle. But for this example, we're going to be assuming that it is at the middle of the vehicle. Okay, then so we're gonna go to I x theta double dot. So this is our general equation number 2. Okay, any question on this equation, on the second equation? Okay, tak ada soalan. Okay. Sekejap. Now we're going to take a look at the third equation, which is the this one is we are actually studying the roll motion. The roll motion now is the pitch motion. Pitch motion, what color? Same thing. So you're going to use a counterclockwise. Going to be summation of moment going to be positive. I y theta. Sorry, this one for pitch we're using alpha. Alpha double dot. Okay. So if you take a look at this one, so this one is actually the side view where we can see that the moment created by the suspension forces at the front axle going to be in positive sign because it's actually when you hit the bump, you're going to rotate in this way. And then the suspension forces at the rear, the one that going to create the negative moment because it's going to rotate in clockwise direction. Okay, so in this one we're gonna use, okay, so we have the same thing, Fs plus Fd for front right, for front left, plus Fs plus Fd for front right, multiply with L divided by 2 minus Fs plus Fd for rear left plus Fs plus Fd for rear right, multiply with the L over 2 equal to I y alpha double dot. So this is the third equation, the most general equation. Okay. Okay, now since that we already have the equation of motion for the motion at the CG of the sprung mass, now we need to go one by one derive the equation for the sprung mass at each corner. Okay, so I'm not going to yeah. Okay. So for unsprung mass, so I'm not going to draw the free body diagram, so you can imagine in your head because we already have 4 unsprung mass for each corner. So the equation are the same. It's just that you need to change the subscript for front left, front right, rear left, right. That's it. Okay. Unsprung. So we try for front left. So it can be FT, FL minus FS, FL minus FL equal to MUFL multiply with ZQFL. Okay, double dot. So this is the okay. Then the fourth. Okay, we have, and then next one we have the unsprung front right. We have FT, FR, multiply FS, FR minus FD, FR equal to MUFR multiply with ZUFR double dot. So this is going to be our fifth equation. So the equation is the same, you just need to change the subscript for each corner. Okay. This one, then we have the unsprung of the left. So we have FT, FR, FS, no, rear right. Sorry. L. So we have FS RL minus FDRL equal to MU Okay. Then we have the MURL, ZURL double dot. So this is our sixth equation. Okay. And then we're gonna have the unsprung rewrite. Okay, so FTRR minus FSRR minus FDRR equal to MURR ZURL double dot. So this is our seventh equation, okay, representing our 7 degree of freedom. So now basically what you need to do is that you need to define all the suspension forces for spring force, damping force and tire force. So basically you have 3 dalam 4, 3 multiplied by 3, so you're going to have 12 definition. Itu saya takkan tulis lah, panjang sangat, okay. Saya nak itu awak komplikan sendiri. Okay, saya akan tulis ni awak make sure awak buat define all FT, FS and FD. Okay, so ini awak tulis. So ini panjang so kita ada 12 equation. 12 equation. Ini awak buat. Okay, and then kita ada lagi satu lagi bila awak buat F ni, kita akan yang kita perlu adalah sekarang ni untuk suspension forces ini adalah kita punya displacement dekat corner. Okay, so basically bila satu bahagian, whenever one side goes up, so another one is going the opposite corner going to go down. And also if you look at these different perspective or different view, so it's going to affect the displacement on that view also. So let's say for example, if you're looking for forward ataupun front view, if this front left going up, front right going to go down. However, if you look at the front left, so for this side view, so front right going to go down, and then this one is going to go down, this one is going to go up. Okay, dia macam effect lah. So this one we need to define. So it's going to be like this. So Z FL, so ZS FR, ZS RL and ZS RR. So basically this one is going to be affect each other. So basically the way that we derive it, easy way to remember it, so just label everything ZS, 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 and then we have alpha, theta, sorry. Theta, and then also this one we have alpha, and remember this one also always has theta over 2, track width over 2. This one is a track over 2, and then for alpha, since that the alpha is L over 2, just L over 2. Okay, now we're going to design between either it's going to be plus minus here, or plus minus for the rest of the equation. Now we're going to take a look one by one. So basically when front left is going to go up, so basically for front left is going to for view is going to go positive value, and then front right is going to go down, okay, plus minus, and then for rear left at the same time when we hit the bump, so the rear left is going to go down, okay, and then this one also going to go up, okay. And then we have for pitch view, so whenever the front left go up, so this one also going to go up. For front right, so when from side view, so front left hit the bump and goes up, so front right is going to seems that it's going to be as if it is going to be going up also, okay. Rear left seems going to go down, and this one going to go up. Okay, we have the full equation. So the berapa tadi? 7, 12, 19. So this one is going to be 19, 20, 21, and 22 equation. So these 22 equations are the equation that you're going to use to model the full car model using the Simulink in your project. Okay, any question? I need to finish early because I need to go. There's something just arise. Okay, any question on this derivation of full car model? Any question?
No, Doctor.
Okay, kalau tak ada, okay, so basically our test one going to be up to full car model derivation. So you can study from the beginning of our classes until now, till tonight topic. Okay, if there is no other question, we can dismiss lah. So betul lah tak ada?